course on calculus RS integration. In this lecture, we are going to see a theorem named integration by parts. So it is one of the most used ideology while working out the problems in integration. Let us look at the technical details of proving this theorem. Suppose we are given the two functions small f and g are differentiable functions on the interval a comma b, and f prime, big F prime is f, which is Riemann integrable, and big G prime is g, which is also Riemann integrable. So these are the suppositions that we made. With these suppositions, we will have to prove integral a to b big F of x small g of x dx is big F of b g of b minus f of a g of a minus integral a to b small f of x gx dx. So this is what we'll have to prove. Okay, let us get into the proof. Let us take h of x to be big F of x g of x. Right? Here we observe that the derivative of big F and big G are f and g respectively. Therefore, big F and G are differentiable. These two are differentiable on the function a comma b. Sorry, on the interval a comma b. This very well tells us that the product of these two functions is differentiable. This is also differentiable on the specified interval by product rule of differentiation. What we get is h prime of x is going to be f of x, f prime of x g of x plus f of x g prime of x. So we get this one, and from the given information we shall write this f prime of x to be simply small f of x g of x plus this is what f of x small g of x. So this is our h prime of x. Let us mark this as equation. Okay, let us mark this as equation 1 and this as equation 2. Now, given that what f and g are continuous ones, f and g are differentiable ones, which means they are also continuous. Continuous means they are integrable. That is given already. And big F and G are okay. If we mark this as equation star, by star we get F and G are continuous also. Continuous on the specified interval a comma b. Hence F and G belong to R on AB. So if f and g are Riemann integrable and small f and small g are also Riemann integrable by the properties of Riemann integration, what we get is your h prime of x is Riemann integrable on a comma b. So this is what we get. Fine. Now we are going to make use of the fundamental theorem of calculus. By fundamental theorem of calculus, your integral a to b h prime of x dx is what? Your h evaluated at b minus h evaluated at a. What is your h prime of x? This is integral a to b. Initially we had a f prime of x g of x plus, okay, let me put this way, f of x g of x plus big F of x small g of x dx, and your h is what? F multiplied with g. This is f of a g of a. Fine. Using the properties of Riemann integration, you can split these things out. Small f of x g of x dx plus integral a to b big F of x small g of x dx is f of b g of b minus f of a g of a, and this gives you the requirements. Just keep only one term in the one side and take the else part to the other side. That gives you integral a to b f of big F of x small g of x dx is f of b g of b minus f of a g of a minus integral a to b small f of x big G of x dx, and this completes the proof, right? And initially while talking about the previous theorems, I have told you that I will talk about some remarks, but I was not able to do that, and now let me do it. Okay, okay, actually this is where we start, right? So in this theorem what we have done is that we have done the integration. We have proved that integral value is a value of an infinite series, right? Your integral value is the limiting case of the infinite sum. This is what I was keep telling from the initial of this topic, and now we have proved that one. Okay, when this is something of different case, we get integral value to be, in either case we get this integral value to be some finite value. Your integral is to be treated as a sum, infinite sum. That is what I was keep telling, and in this theorem we actually proved it. Okay, and this theorem very well tells you the relation between Riemann's Stieltjes integration and Riemann integration. And for example, here I would like to make some example. Suppose you have integral a to b, and supposing my f is x squared, then I'll have x squared, and alpha is also x squared. Okay, what we can do, be it anything, this may be generally what is the derivative of x squared? This is 2x dx, because I have not said with respect to what we are differentiating. So we are going to get 2x dx. So this may be written as integral a to b x square multiplied with 2x dx, and multiply these things and do the integration. This is one way of doing it, and that is what this theorem tells you. Okay, whereas if you come to the next theorem, this is the change of variable, right? So this change of variable means if you have, okay, let me come to the same problem, that is integral a to b x squared d of x squared. Now I would like to change this to some other thing. Let me choose this x square. I am taking it as t. So my integral becomes what? T dt. This becomes t dt. So correspondingly, when x is a, what is going to be my t? T has to be a squared. When my x is b, my t has to be b squared. So the limit becomes a squared to b squared. And this is what we mention it as big A and big B. And this is the value of these two things are going to be same, right? So that is what this theorem told you, and rest of the theorem. Okay, this is from this one, from this relation, if you differentiate this one, you are going to get f of x. That is your f prime, big F prime of x is your small f of x. So using this theorem and the second part of the fundamental theorem of calculus, we did problems in integration during our school days. This is what we remember. Okay, till now we have not derived any formula. If you wish to derive those formulas, yes, of course you can do with the help of the ideas that we have seen. So with this lecture, we are actually coming to the end of Riemann integration and Riemann still just integration on the real line. In the upcoming lecture, we are going to get into the integration of vector valued functions. That is just an idea. With that, we will end this course. Thank you.